Good afternoon, everyone. In first place, thank you, Ian, for your kind introduction and for trusting me with the daunting task of setting up the stage for this panel discussion, but also, most importantly, to keeping the audience engaged after such a delightful launch. I know it's no easy feat, but I'll do my absolute best. So let's start firstly with setting the stage and recapping the actual life cycle of a space mission. It starts with an asset, a payload, atop of a rocket that plunges through the atmosphere, leaving this payload in orbit. Eventually, this upper stage of the launch vehicle will re-enter in the atmosphere, and after this lifetime of this spacecraft in orbit, it will also re-enter in the atmosphere. Now, this helps us understanding that there are two very distinct contributions for the environmental impacts. One that relates to the launch emissions, which is essentially, think of this gigantic exhaust pipe that is essentially injecting these gases through the vertical layer, through the vertical horizon on the atmosphere. And then on the atmospheric reentry side, we also have the contribution from these upper stages of the launch vehicle that inject the payload in orbit, and then eventually and hopefully the fiery demise of spacecraft after their end of life. So now that we have a thorough understanding of these different contributions, I would like to bring you to trends. So, and this essentially relates to the assessment of what is the mass that leaves the surface and reaches orbit, and then when does that mass that reaches orbit re-enters in the atmosphere? And as Antoine Lavoisier once said, there is no mass created nor lost, it is always going to be transformed, and this is exactly what we are looking at. So here we see in red the contribution from satellite-related objects that are launched and re-enter from orbit, and in yellow the launch vehicle-related objects, which are essentially just upper stages of launch vehicles. And here I want to bring your attention to essentially this lag, this delay that exists between launching these objects into orbit and their actual re-entry in the atmosphere. This is essentially related to the fact that there is a mission to be performed, there is a mission to be delivered, and therefore there is this delay between the lifetime of these missions and then the performance of the end-of-life maneuver, before we actually see the re-enter mass increasing. And so my point here is to allude to that we clearly see an increase, especially in the satellite mass launched from the surface to orbit. And then we would expect that this increase to be reflected a couple of years later in the mass that re-enters the atmosphere. We start seeing the increase faintly on the re-entry mass, especially from 2022 onwards, but we expect that this effect is much more prominent in the years to come. The other point that I want to allude here is that we see an increase in the satellite mass launched in the last couple of years. This is obviously related to the deployment of an extensive in-orbit infrastructure, but we don't see the same sort of increase on the upper stages of launch vehicle mass injected in the atmosphere, injected into orbit, which tends to allude to the fact that there is this improved efficiency in these upper stages of launch vehicles, which I believe is a good point to highlight here as well. So now that we have looked at the trends, we may ask ourselves, is this really a problem, or is this just a case of a drop in the ocean? And before moving forward, I want to clarify that in the interest of time in this presentation, as Ian mentioned, my work is mostly related to the atmospheric impacts of reentry, so I'm going to focus more on that part. But I want to encourage you in the audience and also the panelists coming next to also think about the impacts of launch emissions, because these are essentially just two faces of the same coin that need to be addressed in tandem for a proper assessment of these impacts. So with this preamble made, I want to then bring you to this very simple comparative analysis between the mass that re-enters in the atmosphere, between a comparison between natural and anthropogenic sources with regards to aluminum. Aluminum is a constituent, a chemical species that is vastly present in aerospace structures, especially in metallic alloys that are essentially the backbone from spacecraft and upper stages of launch vehicles. And it's also a residual chemical species in meteoroids. So how do they compare with each other? Can we actually say that this is a drop in the ocean? The answer is this rather convoluted diagram that I'm going to walk you through briefly. So each of these bar, which essentially represents the mass of aluminum from anthropogenic sources since 2016, essentially is the summation between satellite-related and upper stage of launch vehicle-related mass of aluminum re-entering the atmosphere. We then can compare it against this horizontal line, which is essentially the mass of aluminum that re-enters the atmosphere from natural sources such as meteoroids. What we see here is, as expected, an increase on this mass level of aluminum from across the years, and this is of course a consequence of the increase of the re-enter mass that I've showed you earlier. But I believe the most interesting point here is that in 2024, for the first time, we are able to conclude that the contribution from anthropogenic sources surpassed that from natural sources to a level of confidence of 95% in this estimate. And so having this in mind, and this logically doesn't mean that there is a negative environmental impact, but this allows us to acknowledge that there is a change in the status quo. So we can with this acknowledge that there is a significant anthropogenic contribution, at least with regards to aluminum in the atmosphere, and this should motivate us to learn more about the environmental impacts. So how can you actually measure this? There are several ways of doing it, and have been attempted in the past decades, I would say. The first of them is through remote sensing. Remote sensing is just an easy way to put together trying to make sense of stuff happening at distance and trying to resolve some quantities of interest. In this case, we see the ATV-1 spacecraft reentry, which is essentially a cargo resupply vehicle to the International Space Station. And here we can see that this is a very good method to resolve the chemical species that re-enter in the atmosphere. Not only the chemical species that re-enter, but also the byproducts of those chemical reactions during thermal ablation. And this essentially, stick to my example of aluminum, you can see that we clearly identify aluminum there, but also some byproducts such as aluminum oxides. This has been attempted again several times with another cargo resupply vehicle such as the Cygnus OA6 spacecraft, and we see again the same characteristic metals which are characteristic from metallic alloys in the structure, and this has more recently been also attempted last year with the European Space Agency campaign that targeted the Cluster 2 spacecraft, that time with a daytime re-entry campaign observation. So this is remote sensing. We can also attempt to do in-situ measurements, which is just a Latin way to say measurements on the spot. It's arguably very difficult to make it in the mesosphere, in that altitude range from 50 to 90 kilometers, if we will, where the actual thermal ablation takes place. This is because high-altitude balloons don't go as high, satellites do not, quote-unquote, fly that low, which makes it very difficult to do it at that altitude. So our best option is to actually measure it when this particulate matter is dissolved into aerosols and essentially is as low in the atmosphere as 20 kilometers, so that we can go there with an aircraft and actually capture those aerosols. There was this very interesting piece of research that came across in 2023 that claimed that up to 10% of the aerosol particles, aerosols captured over Alaska in this measuring campaign contained metals that could be traced back to anthropogenic objects being burned in the atmosphere over the past years. And this is essentially the first piece of evidence that this sort of matter makes it to the stratosphere, and this essentially hit this research area with a sort of a bang. Then we can also theorize about replicating the re-entry conditions in the atmosphere with laboratory experiments, essentially on-ground testing, resorting to some sort of very exotic wind tunnels, where we actually burn these pieces of metal or other spacecraft components, and we further understand how they break up during the reentry event. And here I show you that same example of an aluminum alloy being essentially burned in a wind tunnel, and you can see that in this time lapse that the material firstly melts, and then there is some sort of a film being developed that holds that molten material in space, and then at some point these bubbles are ruptured and the molten material is released. This is a critical understanding of the material science that takes place at this level, that is critical for the further environmental impact assessment, and that to this date still need further development. So with this being said, we clearly have an understanding of the trends. We have some sort of a good understanding of where we are going in terms of reentry, fluxes in the atmosphere. What can be done next? So scientists and the research community started theorizing about what are the actual impacts, in this case, of reentry events in the atmosphere. And I should emphasize here that impacts can be positive, neutral, or negative. We definitely need to acknowledge that there is an impact, meaning there is a change in the status quo with this increased rate of reentries from anthropogenic objects. And I believe the purpose of this panel today is to discuss whether we can say that these impacts are negative or positive. And so, with this in mind, some of the impacts that have been theorized are firstly with regards to global warming. Will these particles that are released and are in suspension in the atmosphere, will they increase the greenhouse effect by entrapping radiation that is reflected from the oceans? Or, on the other way around, will they actually block radiation coming from the sun, contributing to cool down the planet? In another way, will these particles be able to catalyze the chlorine activation cycle, contributing to further ozone depletion in stratospheric altitudes? And some other researchers have postulated that these small particles can also contribute to sediment clouds, to seed clouds at high altitude, which have to this date very unknown impacts in global climate. So with this in mind, I would like to conclude with some food for thought for our coming panelists, with three main thoughts. The first one being that to ensure any sort of intercomparability with regards to environmental impact assessments, I believe it's critical to align in reentry scenarios coming in the coming years. This is something that was done, for example, for IADC to estimate or to theorize about potential scenarios with regards to deployment of in-orbit infrastructure, and I believe there is a clear path for implementing this as well with regards to reentry scenarios. The second point relates to a chemical species. We should have a baseline of what are the chemical species that are currently in the atmosphere and how we are changing that status quo. And thirdly, I believe most importantly, is furthering the understanding of the chemistry and the microphysics of these microparticles, which, as I tried to allude, is essentially possible through in-situ measurements and experiments. And with this, ladies and gentlemen, I hope that the dessert is served. And I now share the floor with Ian to kickstart this panel. I hope you enjoy the discussion. Thank you.